In the previous session, we have verified our simulation results with some observation data and calculate some metrics here to kind of quantify what is the performance of the simulation result. But sometimes you may not need to verify your result with observation data. You may want to verify your result with maybe some gridded reanalysis data to get a picture of how your simulation result, the performance of your simulation result of the whole synoptic weather system. So here, if you see the description here, you can see in the last part, the grid to ops evaluation, it is suitable for measuring the performance of simulation of local scale weather system or regions with fine local refinement. But like if we want to evaluate the general performance or some large scale weather system, then we may want to use like grid to grid evaluation. So basically we just compare our simulation result to other maybe reanalysis grid by grid. So this is the idea. And there are also a few metrics that we used to describe the performance. So we will start from here. And before we introduce the details, I just want to tell you that we need to regrid our simulation data to our desired grid first. So for example, in here, because we have some unstructured grid, right? So these are unstructured grid and like so many hexagons here, like, okay. And then we have some reanalysis data with like 0.5 degree resolution. So this is like simulation, okay. And then we have some here, okay. Okay, these are all, let me type here, 0.5 degree resolution. And this is like reanalysis data. So when we want to compare the two of them, we need to change our grid so that, how can I draw? Okay, here. Okay, so we need to, okay. Here, we need to regrid our simulation result to the grid system of the reanalysis data. So this is the idea of the whole thing, okay? And let me clear the drawing first. And to do the regrid process is actually just interpolation. So we have an unstructured grid and we just interpolate our unstructured grid result to every grid of our desired grid. So, and we have also wrote up the calculation in this interpolate function. So you can see it in, if you go to tutorial 3, the file folder system, you can see the interpolate.py. You need this interpolate.py to call this convert CPAS function. This is a function that we use to regrid the unstructured mesh to any other, like to any structured grid. Okay, so let's run this cell first and to import this function, and then we call this function. And okay, so here we have assigned these grid data and the simulation result data into these variables. Like we need to go back to where we assign them first. So I think, okay, we go back to 3.1.2 and then this is what we do last time, and we need to run them again to assign the variables to these variables. Okay. Oh, I forgot to import any environment. Okay. Let's import the environment first. So import the environment first, and then go to 3.1.2 and then and then run these cell to assign the data to the variables that we need. And then go to the grid to grid evaluation. And then here, let's run this first to see the result. So you can see originally it is like the dimension is something like n cells and time. And now we have changed it to time, latitude, and longitude dimension. This is now becoming a structured grid. And you can see some of the arguments in this function. For example, you need the grid. Need the grid information of your result, and then you need these are the simulation outputs, the output variables, and then you need to define what is your desired grid. So for example, you want to regrid your data to this range of the coordinates. So for example, this is the start latitude and the end latitude is the northern hemisphere. I just specified it. And the start longitude and end longitude is like the whole northern hemisphere. So this is the area of the whole northern hemisphere. And you want to define the grid resolution. So here you need to define it with these n lat and n long parameters. And these are actually help you to define the number of latitude cells and the number of longitude. And I just, because I want it to be like 0.25 degree resolution, so I specified it in this way, times 4, okay. And you also have a method parameter. This method is the method to do regrids or interpolation. And we have introduced barycentric interpolation in the previous session, and there are also another method which is like find the nearest cell to represent the grid of your desired grid. But this is not a really good method. This is a very fast method, but not a good method. So you should always use barycentric interpolation in all your projects and assignments if you need it. Well, I'll just show you here because it's fast in a tutorial. And yeah, I've stated it here, do barycentric interpolation and for all your assignments and projects. So, and then this is the reanalysis data that we want to compare with our simulation results. So we just call this, call this one and then assign it to a variable, dataset variable. And this is the reanalysis data. And then because you can see that the coordinates are a bit different here and dimension is also a bit different. We have time equals to 48 in our reanalysis data. And then we want to do some post-processing to make the simulation data and reanalysis data have the same dimensions and the coordinates. So here we do some post-processing here. First of all, we want to rearrange the coordinates in here because it's from descending order. So we just use the sort function here to help. So this is the latitude array of this one, and then we sort it to ascending order, and then we index it to the latitude. So when we run this, you can see the latitude here, it becomes ascending order. And then because we are only doing the comparison in the northern hemisphere. So here I just extract the useful coordinates from both datasets. For example, in here, this is the geopotential height, 500 hectopascal. And I want to retrieve this variable from my simulation data that has the time dimensions of between these index, and that has the longitude dimension between these index. So basically, I just want to make these two have the same dimension. So I do this approach, okay? And you can always do the post-processing in your own way. And for the analysis data, we first of all want to extract only the northern hemisphere, of course, and then we also extract the time dimension in this range. So you may wonder, why don't I just compare all the time dimension? Like it has 37 in here, right? So this is the simulation data, the dimension. We have 37 time dimension. But as in the lecture have mentioned previously, because this is the simulation data, and we need to have a spin up period for the simulation to reach a balance and stable state. And in this example, I just abandoned the first 12 hours of the simulation. So you can see the time here. Oh, okay. The time, actually, I have outputted hourly variables. So the time is like hourly. This is hourly. So I just abandoned the first 12 hours. So this is what this 12 comes from. And here I just want to make sure the dimensions are correct. So I'd use this assert. And if this condition does not, if this condition gives false, this will give out an error. So you know you're doing something wrong. So here the two dimensions are correct, and the coordinates should be arranged correctly between the simulation and the reanalysis. So after we have done the post-processing, we can try to calculate some metrics to quantify the performance of our simulation results. So first of all, the mean square error and mean error, they are like basic things. I think you all know them, right? So for example, here, okay, so because for this simulation result, the focus is around like the southern China, because there's a typhoon and the path is around this region. So I want to calculate the performance within this region for the root mean square error and the mean error. So I just I'm in here. I just plot a map to kind of see where the region is, and I think this is a good region for me to do some evaluation. So yeah, this is the region that I want to do the evaluation. So I just I slice the data again so that they become the region of comparison that I want. So I just select the data again and use the dot values to change it to convert this is X-array data array, right? So I use the dot values to change it to the NumPy array. And I do the same to the analysis data and just calculate the root mean square error. This is the equation that you should know, okay? And plot the result out. And this is the result, okay? And for the bias and the mean error, I think you can also do it yourself, because you just minus the two of them, and this is easy. And here I want to introduce another matrix, another concept, which is called anomaly correlation coefficient. This is a very commonly used variable when we want to check the performance of our simulation in the large scale weather system. So if you see the equation here, it's basically calculating the correlation between the anomalies of forecast and the anomalies of analysis. And here, this is the F represents the forecast value, and the A represents the analysis value. And the N here is just like the grid step or the time step here. So, and here the C is a new term for you, and this is the climatological value. And when we minus and we subtract the forecast and the climatology together, they will become the anomaly of the forecast. So this is the anomaly of the forecast, and this is the anomaly of the analysis. And we compare them together this is the formula of correlation coefficient. So we just calculate a correlation of the anomalies between these two things. Okay, oh, sorry. And so this is the basic idea of anomaly correlation coefficient. And here, so this is really only the basic equation here. And you can add more complexity to this equation. So for example, in here, if you want to calculate this matrix in a very wide region, for example, the whole Northern Hemisphere, you will need to apply a weight to the data here, to the equation here, because the area of the cell over different latitude is different. We have smaller area when we are at the pole there. So in this document here, let's jump to here. Okay, you can see there is a weight here. The equation, these components are the same. They are for correlation coefficient calculating, but we have added a weight here, and this weight depends on here. It is a cosine phi, I think it's phi, right? And it's actually the latitude. So the area of the grid cell depends on cosine latitude. And this is basically the weight of, the weights. We apply the weighting here to the equation. So this adds some complexity to the equation, but yeah. So let's do this in this section. And first of all, we assign the variables. This is the data array we have. Let's print this to see what it contains. Okay, so this is the model output, contains this variable and these dimensions, and I have already post-processed it so that it contains only the Northern Hemisphere. So we just compare these two directly in the next section, because for ACC, we try to verify the large scale system. So we just use the whole Northern Hemisphere in this part. So again, the same approach, assign the variables, and then to see if their dimensions are correct. And we will have to calculate a climatological value to compute the anomalies of these two components. And for the climatology here, I just take the mean of the analysis data, take the time average of the analysis data, and just take out the Northern Hemisphere. But actually, it's not a good method here because, I just consider that because if we use the data that has a very long time range, the data size will be very large and the process will become slow. And so I just use part of data, but actually it's not a good idea to use only that small amount of data for your climatology. I think you need at least a season to call it climatology, right? So you should do a longer time range. If you really want to do ACC for your maybe reports for your verification. So longer time range, for example, at least a season, right? To call it a climatology. At least a season. But in this example, I just use this short range of time span. Well, but just bear with me because I don't want to make the data size too large in the tutorial. Okay, after I extract the time average here, I get an array that has this shape. This is latitude and longitude. And so after we have prepared all the data we need, we can jump to the calculation directly. So this is a section that I want to apply the weights. The weighting we have talked about before, this depends on latitude and the cosine latitude. So here this is the weight of each latitude, and I want to make an array of this size so that I can apply the weight here to each of the elements in this array. So I create a zero. This is okay, this is an array with this size that all has 0 in it. And I use a folder to just put the weight here to the array. Put the, okay, sorry, the weight here. You can see it is only a 1D array of each of the latitude here. So for each latitude in this array, I put this in the array so that in each latitude of this array, you have this weighting here, okay? And this is a function that I write to calculate ACC. And basically it's a function that you input forecast array, analysis data array, and climatology array, and it just calculated. You may think these are actually just the equation that I introduced you before, and you may read it to make sense of these equations. Okay, so I just run this function and apply this function to all the data that we prepared before, the forecast, the analysis, and the climatology. And also I plot the result. Oh, sorry, I assigned the wrong variable here. The date range, this is the date range. So, and you can see the ACC of our simulation result in the Northern Hemisphere is this way. And of course, the final result is not really correct because I use a really short range of climatology. So, well, mathematically, if you use, I only use like 48 hours for my climatology, and this is really short. So it does not really represent climatology. And you may imagine mathematically, if you have only this short amount of time to do your climatology, there does not have much difference between your forecast value and your climatology value. So when you minus them together here, forecast minus climatology, because the climatology is not really smooth out, the time average is not long enough. This value will easily tend to 0. Like the difference between the climatology and your forecast is not really great enough. So the whole ACC will become lower. So this is not an actual ACC. You need a longer climatology to have a better ACC here. But in general, if a model result has an ACC value below 0.6, well, it is considered the synoptic scale features does not simulated correctly, or the accuracy is not enough. So, so for some well-known meteorological organization, they calculate ACC using like a 40-year data for their climatology. So yeah, that's the difference here. But if in your report you want to calculate this matrix, you may just want to maybe use a season of the data to calculate the climatology. So yeah, I think this is what I want to tell in this tutorial here.